Okay, so last time we finished off getting into this slide. Essentially, the Schrodinger equation is the equation for a wave. Today we're going to end up, fingers crossed, deriving it. But a wave looks something like this. If you have two different functions that describe waves added together, so let's say wave 1 and wave 2, right? They're both wave functions. It's just the amplitude and the wavelengths are different. If you add the two together, you end up getting something that looks like that, right? So if you have a system where this is what you end up seeing, it is called a superposition of the two wave equations, right? So essentially superposition just means a summation of a bunch of, two or more wave functions. The expectation value is the weighted average of the values that can result. And by weighting, it's, the higher the amplitude, the greater the weight, right? So in terms of an average of where you'd expect this to be, it looks like it ends up being somewhat symmetric. So probably have a zero average, but if it weren't symmetric, maybe down here would be more likely because it has more amplitudes, or the amplitudes are greater, and so the weighting towards that value would be higher, right? Or if you remember the square of the wave equation, or the wave equation essentially times its complex conjugate, if you have a complex numbers in there, is your probability distribution function. So these would essentially represent, once you square them, the probability of finding whatever you're interested in, maybe an electron, at that position. And so the expectation value would be you're taking the integral over the entire region, maybe of those two multiplied together. We'll actually we'll be determining, fingers crossed, some expectation values today. Yeah, so today is going to be a full day. Any questions on that? Okay. So part B. And the reason I broke it up into two parts is depending on whether you're using the 9th, 10th edition or the 11th edition, the 9th, 10th, the first half that we already covered is chapter 7. This part would be chapter 8, right? And so sort of segregates it a little bit nicer depending on what version you're using. There we go, that works better. Okay. So second part, we're going to actually be talking now about the motion. So we're going to first work on the wave, or wave equations. Then do the Schrodinger equation, particle in a box, particle in a three-dimensional box. Then we're going to look at vibrational modes, and then rotational modes. Not necessarily all today. We'll see how far we get. So the learning objectives here are very much not complete. There will be more as the document gets more near completion. What's posted up there is a version like this. I'll let you know when the finalized version is up. A couple terms. Okay. So prior to any description or discovery of quantum mechanics, different types of motion people were already interested in. So if you pluck a guitar string, you have it essentially forms these waves. And so if you're interested in being able to describe the movement of the waves of like a harp or a guitar, or even on the ocean, some form of an oscillation motion, there's an equation for that, which is the classical wave equation, right? So you know, draw, we're going to end up deriving that. Okay. So let's say you have your guitar, and you got the two ends of the strings tied down. You're going to draw the simplest type of wave, a standing wave where it's just the two ends are tied and it's oscillating between the two. So this is the same picture that was on that that first, or the slide that we just were seeing. But I'm going to have it here so that we get all the board space. Okay, so we're going to have the horizontal axis be our position. So that's going to be our x-axis. And it's going to range from 0 to length L. I think in your book they use a lowercase l, but to me that always looks like a 1. And so we're going to use a capital L. We're going to try to come up with an equation for the vertical displacement over time. So the vertical value, we're going to use a u of, and then this is x comma t. T for time, x for position along the axis. So an equation that we can use that will tell us how far the string is displaced at any given time at any given position. And so we got essentially two values that have to go in there. Where are we along the string, and then how long, what the time that has elapsed is. Okay. So in terms of our boundary conditions, things that are limiting what the equation is going to look like, our u value, the vertical displacement at, let's see, x is equal to 0 at any time should equal 0, right? It's tied down on this end, and so it can't get displaced vertically. Similarly, u of L, t, the other end also has to be 0, right? Because it's tied down. And that's for both of these are for all-time values. Okay, so because this equation here, or what we know it's going to be an equation, has two different variables, we're going to use what's called the separation of variables method. So we're going to assume that our function u of xt, we can break it up into two functions, one in terms of x and one in terms of t. So I'm going to use capital X to represent the function for the x direction. So it's some function, and then capital T for the time-based function. Okay, so the classic wave equation, second derivative of u, sorry, a little bit more precise, partial derivative of u with respect to x So the reason that it's not a D, and instead we're using these del's, is because the function is a function of two variables, and so we're taking not the exact derivative, but the partial derivative. in terms of how it actually plays out, it works the exact same way. It's just more correctly, it should be this as opposed to a d for the derivative. Okay, so if we plug this in for this equation here, taking the derivative of that equation with respect to x should give us d of t del no. Okay, the reason that over there it was the del and here it's the d is because we're taking the derivative with respect to a function of a single variable, whereas over here it's a partial derivative because it's taking the derivative of a function of two variables with respect to one of them. Little mathy type rules. Okay, now what we would like to do is have it so that all of our time variables are on one side and all of our position variables are on another, right? So what I'm going to do is I'm going to take both sides and divide them by our original function. So if I take this divided by u of xt, this side divided by u of xt. What you'll find is, so divide both sides by x of x, t of t. If I do it to both sides, then they're still equal to each other. What that does though is this t will cancel out that t, this x will cancel out that x. So I'm left with 1 over x of x d squared x of x dx squared is equal to 1 over b squared 1 over t d second derivative of t d squared. Okay. So because each one of these is equal to each other, right, and it's not specifying a single x value that's equal to a single t value, right? All your x are equal to all your t's by this relationship, which means that there has to be a constant value that they're both equal to, right? So essentially the left hand has to give you a constant, the right hand has to give you a constant, and those two constants have to be equal. Another way of expressing that is 1 over x of x d squared x dx squared has to equal some constant, we'll just call it k, and 1 over b squared 1 over t d squared t of t dt squared has to also equal some constant. When we're doing these differential equations, that k value is called a separation constant. Right? We use it when we're doing a separation of variables. It ends up being called a separation constant. Okay, so we can rearrange these. I'm going to move this k to the other side, and this what do we do? Vt. Yeah, I'm going to move the v squared and the t to the other side. So that gives me d squared x of x dx squared equals x of x. Well, let's do k first, right? Yeah. Sorry, other way around. Constant times the function. And t squared t of t dt squared is equal to v squared t of t. Okay. One more step. I'm going to move this to the other side. I'm going to subtract the kx from both sides, subtract the v squared t of t k from both sides. Gives me d squared x of x dx squared minus k x of x equals 0. T squared minus v squared t of t. Okay. So we have these two equations. It'd be really nice to know what this k value is, right? So we can think about k as being sort of one of three different sets of values, right? K could be bigger than one, or sorry, k could be bigger than 0, i.e. a positive number. It could be 0, or it could be a negative number, right? So for possibilities, we got k could equal 0. K could be greater than 0, or k could, be less than 0, right? That pretty much covers all different things that k could possibly be. So we're going to actually try each one of those out and see if we can find something that makes sense, right? So we're going to start with k equaling 0. So we're going to try k equals 0. So let's take a look at this one first. If k is equal to 0, that goes to 0, which means that the derivative, the second derivative, has to be 0. To get the second derivative to be 0, that means you had to start out with, so your d squared x of x, let me put this out more formally, dx squared minus 0 has to equal 0. So that means that this would have to be, the second derivative would have to be 0. In order for the second derivative to be 0, you're looking at a function where x of x would equal some constant times x plus some other constant. Right? If you take the second derivative of that, you get 0. By a very similar argument, right, we'd have t of t equaling, and we can call it a2, t plus b2. Okay, so now what we're going to do is we're going to evaluate this choice using our boundary conditions. Right? So our boundary conditions are when essentially x is equal to 0, this has to be 0. And when x is equal to L, it also has to be 0. Okay? So if it's 0 for all t, one option would be, so we're essentially trying to find u of, let's say, 0 comma t needs to equal 0, which is equal to x of 0 t of t. So this is going to be the case only if either this is 0 or that is 0. Right? But if this one's 0, then essentially this entire, the whole time dependence doesn't make any sense. Right? T, the variable for how it's moving with time, if that's equal to 0, then it's 0 for everything, and then we don't have any sort of a wave. Right? So t of t cannot equal 0. Right? If it equals 0, then we don't get any sort of a meaningful solution out of it. So, from our boundary conditions, that means that x of 0 has to equal 0, and x of L has to equal 0. The equation that we have for x here is a line. Right? The only way a line is going to equal 0 at two locations is if it's horizontal and sitting on the axes. Right? So this would mean that x of x equals 0 for all x. Right? Does that make sense to everybody? All right, this is an equation for a line. If 2 points on that line are at 0, then the line has to be 0 for all values. Okay, which means k cannot equal 0. Right? Setting it equal to 0 means that there's no physical representation, the results has no physical meaning. Right? So if this was the case, you know, if x of x was equal to 0 for all x, what that would mean is essentially we don't have a wave. So it's not going to be a good way of describing a wave. Okay. So we're going to get rid of this. Does everyone have their k equals 0 set down? Yeah. Okay. We're going to keep the first bit so you can see how we're progressing. Okay. So now we're going to try the next option. K being greater than 0. Okay, because we're going to be taking the second derivative, it'll be handy to have k be the square of something. So we're going to start out by calling k equal to little k squared. The reason I'm doing that is you'll see mathematically when we get to a particular step, that's going to make our lives a lot easier. Right? We're also going to say that k, little k is real number. Since now we've been talking about complex numbers, we're going to use k as being some real value. Okay. So if we look at, let's start with x. Looking at this, we need something where the second derivative minus the second derivative of a function minus some constant times that function gets you 0. Right? There's not a lot of functions that that's going to work really well for. And this is for all k values. Right? There's a couple functions that have a repeating pattern. Right? Can you guys think of any when we're talking about derivatives? Where you take the derivative of some function, you get it back, or if you take the second derivative of a function, you get it back? dx, there's one other set. You take the second derivative of sine, it becomes negative sine, or cosine becomes negative cosine, right? We're going to choose the first one, because it's easier to work with, the e to the x. So we're going to try e to the x. So if we take the derivative of e, we're going to call it ax because there might be some constant times our x value. dx. So taking the first derivative of that would be a e the ax. We take the derivative of that, i.e. taking the second derivative, that is equal to a squared e to the ax. So that actually looks really nice for what we're using here, because we're re-representing this, capital K, with k squared, right? So the equation would essentially be d second derivative of x dx minus k squared that's how we're rewriting it, by just substituting capital K as essentially the square of some other value. If you look at this, that looks like a good fit, right? That K value would essentially be your A here. Okay, so if we try this one out here, we get d second derivative e a x dx minus k squared e the ax. Okay, we just did the second derivative of that equation. So I'm going to plug this into, this is what we came out with. So that would be a squared e the ax minus k squared e the ax. We already said that this first part here was equal to 0. Yes? No.
dx squared.
Yeah. Yeah. So, make any other? No. Okay. Oh. Yes, that one too. Okay. Yes, bonus points. Bonus points for both of you. Okay, so we can actually substitute out, we got e to the ax in 2 places. So this could be a squared minus k squared e to the ax equals 0. Okay, the only time that this is going to be 0 is, well, it doesn't quite work out for any of these unless x goes to infinity, but we're bounding it by some L value. So these two have to equal 0. Right? Or well, these two have to be equal to each other. So essentially, your A value has to equal plus or minus K. And the reason plus or minus is because you're squaring them. Right? So A could be the negative of K. Once you square it, that gets rid of the negative sign. So that essentially is going to give us two possible solutions. Right? So x of x could equal e to the kx and or e to the minus kx. Now we can actually, it could actually be a combination of the two, right? The combination could be x of x is equal to some constant times this one plus c2 e to the minus kx. Right, so if you pair them together somehow, when you add the two together, you get something that balances out your a squared. Okay, so C1 and C2 are constants. We now have a function that we're going to try out for our k value on the two boundary conditions. So looking to see, and just like before, if we don't want t to be equal to 0 for all t's. Right, so essentially we have these two functions. In order for it to equal 0, either the x can be 0 or t can be 0, but if t was 0, it would be t is 0 for all t's, in which case we get a meaningless solution. Right? So what we're really looking for is some equation where x can be 0 at the two ends of our string. So we're trying to find x of 0. If we plug x of 0 in, right, we get that's equal to c1e to essentially 0 plus c2e also to 0. E raised to the 0 is 1, so that's equal to c1 plus c2. That one's possible. That one would be if C1 is equal to the negative of C2. Right? That could work out. X at capital L. So you need C1 E L K. Or I guess, sorry, keep this consistent. L plus C2 e to the minus KL. Now, for this to work out, these two both have to be 0, right? Because the only time in which this equation here is going to be 0. These two aren't going to cancel out. Right? So the only way that this works out is if, for both of these, is if C1 is equal to C2 and they're both equal to 0. What that would mean is that x, therefore, x of x for this one is equal to 0 for all x's, right? If this is your equation for x, and that's 0, and that's 0, then the answer is 0 for everything. In which case we get an answer that doesn't really have any physical meaning, and so we're back to the drawing boards. Okay? In terms of what I'm trying to show you is when you're trying to solve some of these, by doing the separation of variables, you can simplify your life, and then you just end up trying a bunch of different conditions. You evaluate them against your boundary conditions, and that's going to tell you whether or not you're on the right track, right? In order for the solution to be correct, it has to satisfy your boundary conditions and have a meaningful result, right? So the first one where k was equal to 0 didn't have a meaningful result. This one also doesn't have a meaningful result, right? If the x equation that goes into here is 0 for all x's, then we don't have a wave, right? If x is 0 for all x's, then the wave can't move. Okay, so we got one last shot. All right, we're going to try, and you can probably guess that it's going to work out because why else would we be doing this? Okay. Try k less than 0. Okay, does everyone have all that stuff? Yes? Okay. Okay. So if k is less than 0, we know we're going to again do the second derivative. It means we're going to do something similar to what we did before, where we made k equal to the square of something. But this time, we're going to make it equal to the negative of the square of something. So capital K, we're going to say, so that this is different from the lowercase k that we used before, I'm going to use negative beta squared. Right, it's just some constant of some variety, and we're going to say that our beta value is a real number, right? No imaginary values tied in there. Okay, so if k is equal to the negative of beta, we can plug this in up here for our x, and we get d squared x of x dx squared is equal, no, all right, not equal, plus beta squared x of x equals 0. We're going to again try what we did last time, the e to the x, right? Because that worked. It worked out fairly well. I mean, we didn't get a good answer from it, but it fit the mold. So we're going to try x of x being equal to e to the x. Okay, so d squared of e to the ax dx squared plus beta squared e to the ax would be, for the same reason as before, this would be a squared e to the ax, this time plus beta squared e to the ax. Okay, and then again, this is equal to 0. We can pull out like we just did before, saying that this is a squared plus beta squared e to the ax for a squared plus beta squared of our original function, right? E to the ax is the function that we're now going to be using for x. So because of this, this has to equal 0. there's two ways that this could equal 0, right? The first bit could be 0, or the second bit could be 0. If the second bit is 0, we're running into the same problem we've been running into again and again. It's a trivial solution. Right? It doesn't really give us any physical representation. So we're going to focus on this one being 0. The way that this one would be 0 is tying in our fun complex numbers. Right? And the reason it has to be complex is because for these to cancel out, you need one of them to be negative. And so your A has to equal plus or minus I beta.
What can both be 0? If 0 plus 0 equals 0 times some function is 0.
Oh, if it was 0, then, if they're both 0? So if they're both, so if you had A and B being both 0, then X would end up being 1 for all values, right? So the A would be 0, so this would be 1 for all values, and then this wouldn't work out. Yeah. So we need it to be able to change, otherwise we wouldn't actually get a wave in there. Okay, so we can, just like we did before, because it's plus or minus, I beta, our function, becomes C1 times E. Now this time it's to the I beta X plus C2 E to the minus I beta X. We can check that this works out. If we take that X, plug it into our equation down here, we should get 0. So we're going to check that the second derivative, d squared c1 e I beta x plus c2 e I negative beta x ex squared. Okay. Sorry. Well. Plus beta squared times c1 e I beta x plus c2 e to the minus I beta x. This should equal 0. Right? This is going back to the equation we had here. It's just we're plugging in the x into that equation, right? So we want to see, does this actually work out? So we need to take the second derivative of this. So taking the first derivative, of c1 I beta x plus c2 e minus I beta x dx. First derivative would be c1 times the exponent, the part of the exponent that comes before the x. So that's I beta e to the I beta x plus c2 minus I beta e to the minus I beta x. Okay, if we then take the derivative of that, c1 I beta e to the I beta x, we can do minus Okay, so now taking the derivative of the derivative that we got, so the second derivative, this would be equal C1 times I squared beta squared e the I beta x. So when we take the derivative of this, we get negative I beta x. The negative will cancel out this minus, so we'll get back plus C2 I squared beta e I beta x. Right? Yeah. I squared is negative 1. So this is equal to C1, right, negative C1 beta squared E I beta x minus C2 beta E to the minus I beta x. We can also write this out as negative beta C1.
Why does it change from negative to positive to negative?
Last one.
Oh, I squared. I squared is our imaginary number. So I is equal to the square root of negative 1. So if we square I, then we get back negative 1. So here we had I squared, and there we had I squared, and so that's what gave us the change of the sign. Okay, so we could write this also as negative beta, pulling out the negative sign and the betas, beta squared, E I beta x plus C2 e to the minus I beta x. You can see that this itself is equal to minus beta squared times our x of x. All right, what's in the parentheses is our x of x. All right? So taking the second derivative of this, yeah.
How did you factor out b squared or beta squared?
You didn't put the squared on
The second term is c cubed b squared.
Yes, okay.
and the top one above that.
There we go. Okay, 4 bonus points. Okay, so this is minus beta squared x. We can plug that back into here. Right, so the second derivative gave us minus beta squared x. So that would mean that this part here is equal to minus beta times x of x. That's this part. First part here is the second derivative plus beta squared x of x. Right? So essentially it minus itself, and that should be 0.
Wait, what? So second derivative of
We just took the second derivative of x. That's what we get. So I'm going to plug that back in over here where we say the second derivative of x plus beta squared x, well, beta squared x of x should be equal to 0. So the second derivative here is minus beta squared x of x. So minus beta squared x of x plus what we had here before, beta squared x of x. It is essentially it minus itself, and so whatever it is, it equals 0. So that's good. And what we come up with for an answer actually works out. So the i's do what they're supposed to do and sort everything out. That still doesn't mean that this is a valid overall solution. It just checks that one particular box. Okay. Right out of board space.
This one.
Well, yeah, but the camera isn't pointing that way. You guys have all this down? Yeah? Okay. So we're still, I'm gonna keep that part up. We'll keep working over here. Okay. So we have C, or sorry, not C, X. This is what we worked out. X is equal C1 E I beta X plus C2 E I minus I beta X. All right. Just bringing everything together. Now, we can use Euler's formula. Which says that E, so whether we're doing plus or minus, I times some value is equal to the cosine of that value plus or minus I times the sine of that value, where the pluses and minuses correspond, right? So if it's e to the plus I theta, then it's cosine theta plus sine theta, and if it's e to the minus I theta, then it's cosine of theta minus I sine theta, right? So we can take our function that we had before, this one here, and I'm actually going to switch it into sines and cosines. There's a reason for it. It might not seem intuitive now, but we're going to do it. Okay, so x of x is going to equal C1 times, replacing this, your beta x is your theta. Right, so this becomes cosine of beta x plus, the first one is a plus I beta x. So this would be plus I sine of beta x. Okay, so that's our first part. Our second part, it's negative I. So this would be C2 times cosine of beta x minus I sine of beta x. All right, and again, the minus here is because there's a negative, e raised to the negative power. Okay, so distributing the c's in and then bringing the cosines together. So I'm going to distribute C1 in here, C2 in there, and then I'm going to bring all the cosines together in one step. That would be C1 cosine beta x plus C2 cosine beta x. check a set of parentheses just to make it easier to see, plus C2, C1, I sine of beta x minus C2 I sine of beta x. We can pull, because we got cosine of beta x here and I sine of beta x here, we can pull the c's out to give us C1 plus C2 cosine beta x plus C1 minus C2 I sine of beta x. Yeah. Okay. Now you don't have to necessarily do this, but a lot of times when we have constants added together, multiplied together, a whole bunch of constants together, a lot of times we're going to just say some other variable is equal to that mash of constants. So I'm going to say let capital A equal C1 plus C2 and capital B is equal to C1 minus C2. So that gives us x of x is equal to A cosine of beta x plus B I sine beta x. Didn't really change from the line above, just makes it look a little nicer. Also makes it a little bit more wieldy. Now we can actually, well, gonna do a quick little change. This I here is the same for both, and so we can do I. And we have a nice sign instead of I sign. And so I minus I. So I'm putting I in terms of the constants because, well, I is a constant. Okay, so applying our boundary conditions, right? So x of 0 needs to be 0 and x of L needs to be 0. So for our first one, x of 0, that would be equal to A cosine beta 0 plus B sine beta 0. Okay, the cosine of 0 is 1. So this gives us A. Sine of 0, 0. A plus 0 equals 0. Therefore, A has to equal 0. Yes, okay. So that means essentially this first part here is gone. Right? If A is 0, it's 0 everywhere. And so that gets rid of that first part. Right? So x of x is really B sine beta x. X of L would then be B sine of beta L. That has to equal 0. We're talking about a sine function, right, which is a repeating pattern when the sine equals 0.
0,
So sine of, we'll call it z, equals 0 at z is equal to 0, pi, 2 pi, and so forth, right? So what we need is some way of getting that to be increments, and we need to be 0, pi, 2 pi, 3 pi, 4 pi, n pi, essentially. So that would mean this beta is a constant, right? So we need the L value is going to have some limits on it. So this is going to work out for L that's equal, well, essentially, all right, one more step. For values where beta times L is equal to n pi, where n is equal to 1, 2, 3, dot, dot, dot. Where n is equal to 0 would mean that x is 0 for all values, and so that's a trivial solution. It doesn't have any physical meaning, but n is equal to 1, that does start to have some meaning. Right? So that one's fairly good. Okay, which means that our beta value, rearranging this to solve for beta, beta has to equal n pi over L. Okay, so there was all that work to find, let's wrap this up. So x is of x will then be equal to beta b sine of n pi x over L. Right, so we have an x value. So we have the equation, we're interested in our overall equation, which is x of x times t of t. All right, we got our x value, but we don't have our t value. But we have found k, right? Because k is negative beta squared. We figured out what beta was, right? So we know what it's equal to. We know this value, okay? And we know that it has to come out to be 0. But I need more board space. So, you guys got all the stuff we just did? Yeah?
Wait, just a quick question about the last
Mhm.
step we did, right? You said any value for x would be that function, right?
Mm-hmm.
But wouldn't it just be like x has to equal L in order to cancel out? So it can't be any value which has to be just L, no? So in the line above we said beta equals n pi over L, right? So that way you would have L's cancel out of sine of beta L, right?
So beta is this. The L's would cancel out, and so you'd be left with n pi.
Okay, so like that's what we want. So wouldn't that put a limit on the x and what it can be? It would have to be L. No?
No.
Let's say x was like 0. No, not 0.
X has to be between 0 and L, right? Because that's the parameter that we set up at the beginning. We're trying to figure out a string that's tied between 2 points.
But then that wouldn't equal to 0 because then it would be like sine of something.
It only has to be 0 at the 2 ends.
Oh, okay. Okay.
So when x is equal to 0, it's 0, and when x is equal to L, it's 0. But everywhere else, it's not.
Okay.
Yeah. Well, other places it could be, which we'll see in a couple seconds. But those are the 2 locations where it has to be 0. Okay. You guys got all this? Yeah? Okay. figuring out an equation for t, we're going to use something similar to what we did before. We saw the last time we could break it up using Euler's into a series of sines and cosines, right? So we're going to try that again for t. So we're going to say, let's see, first I'm going to record that we had our x of x was equal, what do we have, b cosine of, what was it, n pi x?
Sine and pi.
Oh,
x
sine,
over
yeah.
over L.
Sine n pi x over L, right? Just so we have that for reference, right? You don't need to necessarily write that down because you have it on the previous line, but I just erased everything. Okay, so t of t, we're going to try as being equal. We used a, b, I think we had a c in there, so we're going to call this d. Yeah, we had the little c's. So we're going to try d of cosine of t. So that would be the, well, I'm going to write this out and then
Velocity B.
that one's v, that should be frequency. Yeah, okay. That's the v there, right? Because we need the v squared because here we have the v squared, right? And then capital K was negative beta squared, and so we need the beta to go along with the v to make it work out.
Where did that come from? T of T. T of T. Steve. Where did that?
T of t, that's our t function here. We had taken this equation and tried to figure out what it was for k. Doing a similar thing with t, we end up with, you're gonna end up with something that looks like that.
What's K? Oh, like, did we find K?
K, we know that k is less than 0.
Right.
We ended up finding that, well, k we set as beta squared, and then we worked out that beta value was equal to n pi over L. So essentially, capital K would be the negative of what, n squared times pi squared over L squared.
N by x. So we just, okay, so we found beta in terms of x, that's why we had n pi x over L. And now we're trying to find the t.
Yeah, so up here we had b sine beta x. Right, if you look through the derivation we just did, before we determined what beta was, it was b sine beta x. And then we figured out what the parameters on the sine have to be, and that told us what the beta had to be. Okay, so we know what beta is, and we have our, negative beta squared is k. So we know what this value is. The general form of the t equation is the same as the x equation. Right, you have the second derivative of some function is equal to some constant times that function back, or sorry, the second derivative of the function minus some constant times that same function is equal to 0. For the time one, we have an additional constant that's getting chucked in there. But essentially, it's a constant times the function ending up being equal to 0.
So does that mean D equals C1 plus C2 and E equals?
Essentially, but they're not necessarily the same, so it'd be C3 and C4,
Right.
but yes. So you end up doing the same process, and you'll end up with this, and then for the t value, there aren't bounds on it. Right? This function here tells us what happens at x equals 0 and x equals L, but it doesn't tell us what happens at, it doesn't have any t values necessarily equaling 0. So we can't get rid of one or the other of these because we don't have boundary conditions on t. We have boundary conditions on on x, which allowed us to simplify it, but we don't have it on t, and so we're still here. So this is sort of where we were with the x before we applied the boundary conditions and started eliminating things. Joy, you look confused.
I'm not really sure how that equation got there. Like I was following up until we got to x.
Yeah.
Then you just wrote T of T was that function. I was like, not sure where that.
So in the case of the x, you had a part where you had x of x is equal, I think it was a cosine of beta x plus b sine of beta x. Yes?
Yep.
If you follow the derivation through all those same steps for t, you end up with this. At that same line.
So basically beta is just like it's being replaced by omega n or wn.
Yeah. Where this omega n has beta in it. It's essentially beta v.
So what do we mean beta v squared? Because we're replacing k v squared? Because we're trying to replace like d squared t of t over dt squared minus k v squared t of t. So we're I don't know. So okay, we're trying to figure out what k is. K is negative v squared. That's in the place of beta x to wn. And then we have v. In the original equation we have v squared. So do we need to match that up, or since we're taking beta squared?
So we could take this equation here, rewrite this as being d squared t dt plus beta squared v squared t of t. And essentially because the beta is a constant and v is a constant, whatever you do to one, you're doing to the other.
So you can get rid of the square.
You can't get rid of the squared.
That's what
Yeah, that's why isn't omega b squared over b squared? B squared.
Because it's the same reason that this is beta and not beta squared, right? It's because we took the second derivative. Is everyone confused on this part? Yes?
I mean, I am.
Okay.
So I got the part where you're translating from x of x to t of t, up until you have the parentheses, and I'm not sure how they are. Okay, t and x, and then wn equals beta. That's why I'm confused. How is wn equals beta? In those two lines, right? T of t
Okay.
max of x, everything maxes out until w and beta.
So why don't we do how we get to the t is equal to d cosine omega n, right? So we'll just do it explicitly. Okay.
Maybe it's because why v is the square.
Yeah.
We'll get there.
Oh.
Okay, so okay, so we're going to apply the same thing that we did for x to t. We end up with e to the at instead of x, right? So if we take the second derivative, we get d squared e to the ax over d t squared, because we're doing the time one, plus beta squared b squared e to the ax. Okay, so if you remember previously this thing here, taking the second derivative of this was equal to a squared e to the a, and it would have to be t because we're doing time, right? From before, same derivative of e raised to constant times the variable. So this would be plus beta v squared e to the a x. We can rewrite this as a squared plus beta squared v squared e, no, not x, sorry,
On the left
a
side
t, a,
left side
yes. Sorry, I much prefer x to t, but, oh. T, okay, t's gonna be our variable. Okay. So this has to equal 0, because that's what we had over here.
beta squared.
Hmm?
Beta squared v squared.
Yeah, beta squared. Yeah. So this has to equal 0.
Wait, how can you take out v squared if it's on the left term?
Hmm?
Of those two terms, right? V squared is only on one of the term. So how can you like factor it out?
What do you mean?
So it's a
It's
squared
the-
e to the at plus
Yeah.
beta squared v squared e to the at.
Yeah.
So only commonality is a. Oh wait.
The commonality is e to the
E to
at.
the
So I pulled that out.
okay.
You good?
Yep.
Okay. So, in order for this to work out, A has to be plus or minus I beta V. Well,
A equals plus or minus.
yeah. Well, I guess we could combine, well, if you square this, that would be the same as I squared times B squared times B squared. Right? So if we square it, if this is true, A squared, sorry, and that would be equal to plus or minus, whichever one you want, squared. So essentially you get back plus I squared, beta squared, b squared. Right, and so that would be, in the end, negative beta squared, v squared. And so when you add the two together, you get 0. Okay. So, T of T would be equal, because it's plus or minus, we'll do C3 e to the I beta T plus C4 e to the minus I beta. No. We're replacing the A with what is equal to, I forgot the V. V T plus C4 e to the minus I beta V T.
Wouldn't that be
T of T.
D of T. I do much prefer working with X. This is the way it is. Okay, so we can apply that same Euler's formula that we had before, right? So this would be T of T is equal to C3 cosine of beta v t plus I C3 sine of beta v t. That's the first part. Plus C4 cosine beta v t. Ran out of room, so sorry, minus I C4 cosine, no, sine of beta v t. Combining them all together, so I'm going to take my cosines, bring them together, take my sines, bring them together. T of t is equal to C3, and then you see I got cosine of the same thing, so this sort of putting two steps together, C3 plus C4 cosine of beta VT plus IC3 minus IC4 sine of beta VT. And then we just say, what are we using? D and E. So we're going to let D equal C3 plus C4 and E equal I C3 minus I C4. Now, we already know what beta is, right? So, because beta is equal to n pi over L, we have this beta V, so we could say we're going to replace the constants with an omega n is equal to beta V, which is equal beta is n pi over L times V.
Hold on one second. This is where I got confused when you asked this one. So you're just like assigning a letter
Mm-hmm.
to make it simple.
Yeah, because right here I got two constants times each other, so I can replace that with one constant.
So what about the T?
I didn't include t here. So this would then be
Also, it would be just a WNT.
t of t would then equal d cosine of omega n t plus e sine omega n t, which is what we were doing before. Okay. Questions? Okay. So the D and the E value, just like the B value, because it's a sine slash cosine wave, anytime you have a sine or cosine wave and you're multiplying it by a constant, that makes it higher, so that's essentially the amplitude, right? So this B, D, and E are all amplitudes, right? How big is going up and down. Okay. So, does everyone have all that? Yes? Okay. Okay. So that's what B was equal to. T, we had D cosine omega n t plus E sine omega n t, where omega n is equal to beta b, which is equal to n pi b over L. Okay, so we have our two equations. We're going to plug them back in here and see what the U equation actually looks like. So U of x comma t is equal to b sine n pi x L times d cosine omega n t plus e sine omega n e. Yeah. Okay, we can combine so I can distribute this B into both. So then I'm going to move the sign to the other side. So I'm going to let F equal G times D. And we're going to say G is equal to B times E. Just doing this to keep the number of constants that we have to a minimum number that we have to write in. So that means U of x t is equal F cosine omega n Okay, and then that's still for n being 1, 2, 3, 4, for n's being integers. Okay, now there's a harmonic addition theorem. Okay, which is used to combine sine and cosine values together when they have this, when they're of the same variable, right? So according to the harmonic addition theorem, if we have a cosine of x plus b sine of x, that's equal to some other value, a cosine of x plus alpha. And that's where a is equal to the square root of a squared plus b squared. And alpha is equal to the inverse tangent of minus a over b. All right, just one of them trig theorems that we're going to use. Okay, so we can actually combine these two together, right? You can see that this forms generally that, where the f is the a, the g is the b, and then the omega n t is essentially x, right? So we can use this theorem to bring this down into just one variable, or sorry, one equation of a cosine. The reason we're doing that is it's easier to visualize than trying to visualize the sine and the cosine added together. So, equals, we can call it C cosine nt plus some value and sine and pi x over L. Now this is for a single n value. All right, that's if we're picking like n equals 1, n equals 2, n equals 3. So that would be if we're looking at a single standing wave, right? If we're looking at something that's more complicated, so a superposition of a bunch of different waves, then we would just add them all together. So this is for a single n. And that's n equaling 1, 2, 3, dot, dot, dot. The function, if we have a bunch of superposition, or a superposition of a bunch of functions together, so a more complex wave, this would be equal to the sum of all the waves that go into it from n equal 1 to essentially how many ever you have, Cn cosine omega n t plus Okay. So if we graph that out, so this ends up giving us this function. If we use n values, so if our n is a greater value, you know, n is larger, you know, let's say it's a 2, then we have this being a 2, which means between our 0 and our L, we have something like that, and we'll have a middle value where it's equal to 0. That is a node, right? You might remember from physics or gen chem. The location where it's the stationary location where a wave is moving between, that's called a node. The wavelengths, or I guess the V, where we got, okay, yeah. So where n, couple terms, when n is equal to 1, that is called the first harmonic. And equaling 2 at the second harmonic, and equals 3 is the third, and fourth, and fifth, and sixth, and seventh, and so forth.
As you increase n, you're gonna have n minus 1 nodes.
Yes. Okay, so that is the classic wave equation.
So if you were to ask us, like, when n equals 3, you have to like do that at n equals 1, n equals 2, n equals 3, and then add this up.
Yeah, or draw out what it looks like when they're added together. Okay. I'm gonna take a quick